doesn't make it
it should affect the rate of wind. The only thing that we're talking about is pressure, the elevation. We change how fast it will work. So that's how fast it would work. It would boil faster.
It'll boil faster but not cook.
But it would not cook faster. So adding salt.
Yeah. It'll cook the same amount from boiling point. It's like it'll boil faster, but once it starts boiling, if they're both boiling, it doesn't cook faster. It cooks the same amount.
Okay, so
but to get to boiling,
says that adding salt
it makes
to
it
water,
boil faster.
A makes this water salty.
Well, obviously.
Yes.
Make the water salty.
It's all of them.
Who says B makes the water boil faster? Okay, who says C cooks the pasta or beans faster? Yeah, so you know that A is correct. It turns out that C is also the correct answer too. Okay, now what's happening is we know that pure water has a boiling point of 100 degrees. Does the boiling point of this water change when you add salt to it? Yeah. So, is this solution going to have a higher boiling point than 100 degrees or a lower boiling point? Higher. Yeah, so it turns out the boiling point of this is going to be higher than, greater than 100 degrees. Okay, so since the temperature is greater, will this boil faster than this one?
No.
Nope. Yeah, this will actually start boiling before this one does. Now, since the temperature is greater than 100 degrees, let's go to part C. Is this going to cook the pasta or beans faster? Yeah, it will. Okay, no, because the temperature is higher, so it should cook the beans and pasta faster. So remember last semester, Chem1B we talked about if you go up to high elevation, say Lake Tahoe, the boiling point of water is lower at that higher elevation than it is at sea level. So that's why you have to adjust your cooking times, actually longer cooking times in Lake Tahoe, because at Lake Tahoe, the boiling point is lower, like 95 degrees somewhere. Okay, let's go on to the second question. You're not paying attention, and you keep on adding salt to water, so at some point, the water is still salt. The salt will continue to dissolve in the water, or C, the solution will become saturated, no more salt dissolves. Okay, so who says A? The water, yes, which one? No more salt dissolves. Who says B, the salt will continue to dissolve in the water? No. Who says C, the solution will become saturated, no more salt dissolves? Yeah, so at some point, if you keep on adding salt, no more salt will dissolve. Okay, now, what does saturated solution mean?
More of the solute than the solvent.
George?
More of the solute than the solvent.
Well, see, maybe we need to do this too. So let's do a couple of definitions. Okay, so we know that a solution consists of a solute. And a solvent. So the solute can be defined as a substance present in the smaller amount, and the solvent is a substance present in the larger amount. Okay, so this is the smaller amount presence in the larger. Now for a saturated solution, that means
That they switch roles, maybe?
not necessarily. Because see, what we're saying here is that the solution will become saturated. That is, the water will become saturated with the salt, and no more salt dissolves. So at some point, not necessarily equally. John?
The maximum amount of solute that is
Yeah.
dissolved.
So like John says, a saturated solution is when you have the maximum amount of solute which dissolves in that solvent. Okay, so that's what saturated means. Okay, so you have the maximum amount of solute dissolved in the solvent. Now, the textbook actually shows a table which shows the solubility of sodium chloride in water, and that's on page. That's on page. That's on page. I know it's in this book somewhere. Let's see. Okay, so that's on page 443, chapter 13, in the textbook. So they look on page figure 13.3 on page 444. It shows. It shows this table of solubility in grams of solute per 100 grams of water versus temperature. So that is the solubility versus the temperature. And for salt, it's here's the 50 mark. This is in grams of solute per 100 grams of water. And the temperature ranges from 0 to 100. Okay, so for salt, it turns out that 40 grams of NaCl is soluble in 100 grams of water. Okay, so that's actually the maximum amount of salt which can be dissolved in about 40 grams per 100. 40 grams of salt per 100 grams of water. So that's for salt only. So there's this table, or this diagram also shows some other compounds, for example, potassium nitrate, sodium nitrate, and so on. Okay, so although salt is soluble in water, we can't dissolve an infinite amount of salt in the water. At some point, that solution becomes saturated. We can't dissolve any more salt in the water. Okay, so let's go to the next slide. How can we get more salt to dissolve in the water? Add more water. Okay, so let's say we have a saturated salt water solution. How can we get more salt to dissolve in the water?
Or more water. Heat it up.
Yeah, one way is to heat it up. So in figure 13.3, it shows that as the temperature increases, a little bit more salt can be dissolved in the water. So raising the temperature of the salt tank can get more salt to dissolve in the water. So cooling down the water is not going to work. What are part C at? Using more water. So if you have a saturated solution, if you add more water to that saturated solution, is the solution still saturated? No. Okay, so let's say you have 40 grams of salt dissolved in 100 grams of water. let's say you add another 100 grams of water. Now you have 40 grams dissolved in 200 grams of water. Is this solution going to be saturated? No. So can you get more salt dissolved in that water? Yes. That's what they said. Okay. Actually, that should be figure 13.3. Yeah, figure 13.3. Okay, so in general, solids are more soluble in hot solvent than in cold solvent. And then later on in the semester, when we look at equilibrium principles, we'll learn the reason why most solids are more soluble in hot water than in cold water. Let's go on to the next part. Have you guys heard the company SodaStream? Make your own soda or carbonated water?
Yeah, at Costco.
Has anyone ever tried it? Is it any good?
It's pretty good.
You can make your own soda, can't you?
Yeah, you can make your own energy drinks too.
Really?
Yeah. And at Costco, they have like a big canister for like cheaper.
Okay, so when you make soda or carbonated water, you got to get carbon dioxide, CO2, to dissolve in the water. So how can you get CO2? Go on. Would you expect CO2 to be soluble in water, first of all?
No.
So why would you not expect CO2 to be soluble in water? Okay, we know water is polar. Is CO2 polar or non-polar? Yeah, CO2 is non-polar. So again, we know that CO2 is non-polar because the structure of CO2 looks like. Okay, so what's the Lewis structure look like? It's like a water one. It's like a water molecule. Yes, double bond between carbon atoms, low pairs in there. Make sure you track all. Now, what is the shape of the CO2 molecule? Yeah, so it's linear. So in BSEPR theory, we treat a double bond the same as a single bond. So this is a linear molecule. So since it's linear, it's non-polar. So how can we get more CO2? Okay. Now we can use a solution process